This event is brought to you by Data Talks Club, which is a community of people who love data. So we have, so first of all, we have a Slack where we can talk about different things, data-related things. And we have weekly events. And this is one of these events. And actually, to find out more about the events that we have, there is just a page in our website called Events. And today, what we have in our agenda, today we will talk about building scalable end-to-end deep learning pipelines in the cloud. And actually, we have two types of events. So today, this is a webinar event where we have slides and the topic is very technical. But then we have less technical events on Friday, where it's more just a conversation around certain topics. And then on this Friday, we'll be talking about public speaking. And then you can go to our website, check what we have prepared for the next weeks. And if you want to stay informed about our future events, there are multiple options. You can do this. So first, of course, you can register in Slack. Then you can subscribe to our newsletter, and then every week we will send you the plans, the events you can register for. And then the last option, now we will be streaming all events to YouTube. So you can just subscribe to our channel, and then you will get a notification when a new stream starts. That's all from me. So if at any point of time today you want to ask a question, there's a pinned link in the live chat in YouTube. So just link on that, click on this link and ask a question. And then after the talk, I will ask all these questions. And yes. So I think with that, the intro is over, and the floor is yours now.
Okay. Thank you very much for introduction, Alex, and thank you very much for hosting the event. And thanks everyone for coming. So I'm Rustem, machine learning engineer at Instrumental. And today I want to tell you about how to build scalable deep learning pipelines in the cloud. So some takeaways which I want you to take from this talk is first is cloud-native orchestrators are very convenient to organize complex pipelines which utilize different services. And there are a lot of different services when you're using cloud at your disposal, which you can use, and it will depend on your context. And it's actually very easy to start, and you can actually start doing it even for research projects. So first, let's look at how usual data science process looks like. So first, we start with business understanding. We try to define problem, identify data which we can use. Then we try to get this data and label it and explore it. Then we can actually build a model on top of it. After that, we can operationalize the model. And finally, we can get feedback from the customer. But actually, the last three steps is a very iterative process. And we want to be able to get early customer feedback to understand whether what we are doing is correct and useful. At the same time, we want to be flexible in case our data changes, our model changes, and so on. And finally, in case we're not making a standalone product, but it's actually part of larger product, we want to be able to integrate with existing infrastructure. So we don't have to host it in a different area. So in our particular case, I will explore how Serverless will help us to do so. So first, I want to tell a couple of words about Serverless itself. So here you can see spectrum of different ways of application deployment. On the left, we have on-premise. Basically, it means that we have to control the whole stack, which is blue here. And we gradually come to SaaS, where we don't control anything. With Serverless, I particularly will look at three basically columns here. It's container as a service, platform as a service, and function as a service. Where function as a service, we control only the code. With container as a service, we control container and code. So basically, to put it shortly, serverless, in more general term, it's something which will scale on demand based on your consumption. There would be no upfront costs, and there will be pay-as-you-go pricing, and no payment for idle time. Small asterisk, I will cover it later. And there are low operational support. It's very easy to define it as a configuration and easy to deploy. And there are a lot of integrations which allow you to integrate it with existing infrastructure. So in short, why is serverless would help us in building deep learning pipeline? Basically, because there is low operational support and no upfront costs, it's very easy to start, even for research project, because you don't pay for what you're not using. Because it's defined as a code and there are multiple integrations, it's a very flexible infrastructure which you can easily change, add new steps, remove some steps, and so on. And because it's scalable and has could be integrated with other parts of the cloud infrastructure, you can integrate it with production very easily. So in this production pipeline, I want to look at three main steps and how they can be organized. It's data preprocessing, deep learning, machine learning training, and inference. So with data preprocessing, basically we need to gather data from multiple sources. And the challenges is that we may need to utilize multiple frameworks. We need to be able to scale based on load. And we may need to combine different processing types. With training, usually we just need to train and publish the model. But if you have a more complex case where, for example, you want to check multiple sets of hyperparameters, or you have some semi-automatic logic where you actually need someone in the team to accept the model before it goes live, then it kind of makes it more complex. And the challenges here is that GPU instances are expensive, and also there is a high level of uncertainty compared to normal software engineering. And finally, the inference is where we want to make predictions on the upcoming data. Here, because it's usually a customer-facing workflow, it has all limitations for it. So we need to have low latency, be able to scale based on load, and be cost-effective. And we may need to handle multiple frameworks, model versioning, and have some way of rolling out new model because it's you cannot just deploy new code in this as you can deploy a new model as you do with code. So first, let's take a look what we actually have in the cloud and what we actually can use. So first, let's start with container and functions as a service, basically computing. So although they're different, we could call it like a serverless cluster. It's a computing cluster of worker which will scale based on your consumption. And you only need to define code and launching configuration. So you don't need to handle underlying logic. From this perspective, although different services more or less work similar, but they're kind of different. So for example, with AWS Batch, which is basically a cluster which would scale based on load. So for example, it wouldn't have like perfect idle time. There is perfect container as a service, which is Fargate and SageMaker, which will just create 1 VM per job, and AWS Lambda, which starts 1 worker per job. So first is AWS Batch. In short, you just define, there are multiple components, but the main part is that you have a cluster and you have cluster manager. And based on size of the job queue, it will scale your cluster and it will try to optimize it to run jobs in parallel. But basically, it won't promise you 0 idle time. So there may be a case that after the job is finished, cluster stays for some time. AWS Fargate, which is perfect CAS service in a way that you just define Docker image, and then it will run it will start 1 VM per job, but it's limited to only CPU instances. With Batch, for example, is very flexible, so it's not limited. It cannot use like some of the instances, but usually it can use almost all of the instances. With SageMaker, there are 2 services which can be used. So first, there are processing jobs. Basically, it's similar to Fargate that it starts 1 VM per job. The difference is it can only be used for on-demand processing. Fargate could be used as a web server. And the limit for all Sage microservices is that they can only work with ML.instance types, which usually cover most GPU and CPU instances, but not all. And the main advantage is that processing jobs can mount S3 buckets as disks, so you don't have to download data. Uh, and training jobs. Training jobs is similar to processing jobs. The difference is that it's focused mostly on model training. It's similar to processing jobs, but it has additional advantages. Basically, it handles monitoring, hyperparameters, data import, and model export for you, so you don't have to handle it in your application code. And it has support for spot instances. And one of the challenges when using spot instances is that your instance can die, and you want to be able to return to training from the checkpoint. So SageMaker will handle it for you. And finally, AWS Lambda, where it used to be that you needed to define code and libraries, but after reInvent 2020, now you just you can also define just Docker image, and it will start right away. In short, Lambda works as when service gets incoming event, for example, file change in S3 or new message in SQS or Kinesis, it will take configuration from which you defined, will take a container from the container pool, will start a worker, process the event, produce a response, and then it will keep this container warm for some time. So if new event comes up, it will be processed by warm container, so it doesn't have to start it. So this is like warm and cold logic is one of the challenges with AWS Lambda, because otherwise it's like very scalable. So if we put all the services together and compare it, we will see that Lambda basically is like it has perfect startup time, pricing is per 1 millisecond. It has nice CPU and RAM limits, but it has some limits. So Lambda is the most scalable of them all, but it's also limited in terms of configuration. Batch is basically the most flexible, but it's the closest thing to your usual cluster, where you basically, although like you don't have to scale it manually, but you basically cannot scale it as fast as Lambda. And you have SageMaker and Fargate, which scale pretty fast, has nice pricing, and have their own limitations. So yeah, for SageMaker, Fargate, and Batch, the pricing is per 1 second, but you have to keep in mind that minimum with AWS instances is 1 minute. So if your job takes, for example, 20 seconds, you will pay for the whole minute. So if you have short processes, it's better to use Lambda. If there are long-running processes, it's better to use Batch or Fargate or SageMaker. So now let's take a closer look at what type of instances we can actually use for our ML jobs. Because one of the one of the challenges is to understand like what type is suitable for a workflow. So for training, it's obvious usually that like if we're working with deep learning, we have to use GPU, TPU. For inference, there are multiple things we need to think about. So for inference, both CPU and GPU could be used. And there are multiple things to take into account, including speed of a single inference, speed of batch inference, how much does it cost to actually run the inference, because GPU will be more expensive, and how fast can you scale if you need to process peak load. So here you can see the table is of running Inception V3 on different type of instances and AWS Lambda, with basically sorting by inference time from the slowest to the fastest, from Lambda to Inference 1 instance, with costs of predictions and cost per month. We can see that Lambda is the slowest option here. Like it's 338 milliseconds compared to Inference striking 9 milliseconds. But you have to keep in mind that all these instances will be based on like servers. So you have to pay for the whole month. So actually, if we look at how much money we pay per month for one instance, we will see that for the same price, we would be able to get some amount of lambda predictions. And you can see that if, for example, we have less than 1 million predictions per month, which could be the case for pet project or when your project just starting, it's actually more cost efficient to use lambda. And here we can see that it's only one instance, and lambda will be able to scale based on load. With instance, you will have to implement a more complex logic. So the thing which I want basically to cover with this table is that you can use different services for your application, and you have to think about your context, whether you want it to be fast, whether you want it to be scalable, or whether you want it to be cheap. So now let's take a look at, like we compared instance. Now let's compare CPU services, which I mentioned for computing. So it's Lambda, Fargate, and Batch when using C5 instances. So we can see that Lambda is the most expensive. Basically, it's 2 times more expensive than Fargate, and a lot, almost like several times more expensive than a C5 spot. Like, why would we use Lambda? It's so expensive. But as I mentioned before, with Lambda, pricing is per 1 millisecond. So it's very optimized for short-running processes. And also with Lambda, you can be sure that you don't have any idle time. So you only pay for what you're using. With Batch, you will have some idle time. And with Fargate, you basically, if it's under 1 minute, you will have to pay for the whole minute. So next, let's compare GPU, specifically P2X large instances, which is K80 GPU NVIDIA. So if we compare SageMaker with Batch, we can see that SageMaker for almost the same instance is more expensive than Batch. And although like SageMaker prices were reduced recently up to 20%, it's still somewhat costly. The difference is very similar. With SageMaker, you are sure that you don't have idle time because it's contained as a service. With Batch, you will have some idle time because server will exist for some time. And it's something which you have to keep in mind. So now let's take a step back and like look at the services which I mentioned. Basically, when you implement deep learning application specifically for training, usually you run it on one instance, like where you run the whole workflow. But maybe sometimes it's not the most efficient because you have different steps in it. Like sometimes there is data gathering, data preprocessing step, and GPU is only used for training itself, not for other steps. And we can actually slice this application to run it on different services which are more suitable for the specific case. For example, we can use some fuzz to gather data because we can do it in parallel, and it will work very fast. If we need, for example, to parse 1,000 websites, it will be faster to do via fuzz. If we need to preprocess some complex data like image data or satellite imagery data, we can use multi-core CPU to process it faster. We can run training only on GPU, and then we can do some other tasks like model upload on CPU. Basically, we can look at it as minimizing idle GPU time, because applications which don't use GPU, that they will just waste your GPU, and it's very expensive. So next, let's look at platform as a service, basically as a way to how can we organize this kind of like modular approach, modular application where we have different computing services. So here we utilize microservice architecture. So we will have to use some connectors between services to do so. For short running process, usually the best option to use REST API. If you have long running asynchronous process, you can use either event queue or orchestrator. The advantage for orchestrator is that it's easier to trace the process and handle complex intermediate logic, which is usually the case with deep learning, where you either have like additional checks or you may need to be able to handle semi-automatic logic. So if you're using orchestrators, there are some advantages of using cloud-native orchestrators, is that you have native support for the computing services which I mentioned. There is central monitoring, logging, and tracing, so you can easily see like how your application ran through your workflow. and it can scale on demand. Asterisk as always, not for all services, but usually. So first, I want to cover the Amazon Step Functions. It's the oldest service in this bunch. Basically, it's a graph-based workflow. It can have loops. It can handle different processing nodes, have support for the services which I mentioned and more. It can have a custom error handling. You can run tasks in parallel, and you can add steps for waiting and scheduling. And the pricing is pay as you go. Next option is to use SageMaker pipelines. It's a DAG-based workflow, meaning that you cannot have loops here. You can always have like a streamlined workflow. Basically, it's more limited in terms of services which it can use, only to SageMaker services like processing, training, and data blue. The advantages here is that the main advantage is it has data and model lineage tracking, meaning that your pipeline becomes part of your model artifact, and you can easily track how your model was trained. You can always do it with step functions and other options, but you would need to do it manually. Here it's implemented for you. And there are some steps which were designed specifically for training process, like human review step, where you can design like a user or like engineer to review model performance and decide whether you want to proceed with registering model or not. And it's free, asterisk here. So it's free only but because you're using SageMaker services. So it's free because you are limited in terms of services which you can use with it. And finally, managed Apache Airflow, which was announced in reInvent 2020. It's also DAG-based workflow. It's our usual Airflow, which is just hosted. It's very flexible. Anything you can do with usual Airflow, you can do with managed Airflow. It's very, very flexible. The main issue is that it doesn't scale automatically. You will need to do it manually. And second is it doesn't have pay-as-you-go system, so you pay per instance time. So if we like put them all together and look at like how they compare to each other, we can see that SageMaker pipelines is best if you have if you just want to start with using workflow for your research, or have some semi-production workflow which require more validation from engineer or user. Step functions is usually the best when you have to integrate different services and have higher tight integration with production infrastructure. With Airflow, I would say the main advantage is that you can run it locally. And if you have some existing Airflow pipelines, then it's best to use managed Airflow, even though like you won't have like full pay-as-you-go experience. So for the scalable pipelines, we will use serverless approach, where basically we will use AWS Lambda for short parallel processing, Patch for heavy processing and training jobs, SageMaker for training jobs and distributed training, and finally Fargate for long-running processing, basically for data. And we will use step functions to glue this all services together. So let's look through how the steps which we mentioned before and how they can be implemented using the services which I mentioned. So first is data preprocessing. Basically, in short, you can kind of use step functions to separate it in having SageMaker for processing, for heavy processing jobs, and having some scalable processing for processing any step which you can parallelize. With batch Fargate, it's somewhat similar. So you can use it for processing. The only difference is that you would need to implement a logic for preparing data and parameters and uploading them to S3, passing some parameters to batch Fargate, and then handling output data on next step. So where would it work? So if you have peak loads and you need to scale automatically, or if you have some complex logic for data preprocessing, it would be best. Or if you want to have a more customizable pipeline where, for example, you want to utilize multiple frameworks or multiple programming languages, and you cannot use one Docker to run them all. So where it wouldn't work. So if you need to run synchronous data processing workflows, which can be run like on one image, then it's best to call AWS Lambda. If you just have a workflow which doesn't consume much and you just want to process it faster, then having something like SQS Kinesis plus Lambda would be a cheaper and faster solution. So repositories to check, it's here you can see the link to repository. I will share it in the end, where you can see the serverless configuration files, which you can basically use to deploy the patterns which I mentioned to your AWS account, play with it, use your Docker images and so on, and see how it works. Next is training. So with training, there are multiple ways how we can organize it. First, we can use SageMaker. With SageMaker, the main advantage is that basically a lot of things which will be handled for us. So it's higher parameter tuning. It's the input data will be mounted to our disk, so we don't have to download it from S3. Checkpoint will be handled for us. And uploading of parameters and metrics, as well as model export, also will be handled for us. And we can run distributed training when we need to train the model on multiple instances. Alternatively, we can use batch. So with batch, as you remember, like the pricing will be better, and we will be more flexible in terms of choosing instances which we want to use. But we will need to implement all the things which I mentioned manually in case we need them. So we will get higher flexibility, but we will need to provide parameters, checkpointing, and data, and handle model export after the training step. Finally, one of the options is to use external infrastructure. It could be the case where you want to use on-premise GPU, or you have some other service which provides very, very cheap GPU instances, and you want to integrate them in your production infrastructure. In this case, the functions will be like glue, which prepares data and parameters, and external GPU will check it, will find that there is a task, it will process it, upload the result, and then the workflow will continue, and it will register the model which was trained in your infrastructure. So it's a kind of a way of having hybrid infrastructure in your application. So it increases complexity, but in case your model is very expensive to train, it can save you money. So basically, how do you know if this would work for you? So if you have some occasional training jobs, or if you have some custom logic, then it works best. Or you want to integrate external infrastructure, where it wouldn't work. If you have extremely simple models and you want to train them in a synchronous way, in this case, it's better to use cluster because step functions don't support synchronous workflows. And there is some additional idle time before the worker can start. Or if you want to maximize training speed, because when you have existing cluster, you don't have any startup time. Same repository where you can see basically different configurations and check how they work. And finally, the inference. So with inference, like let's say we decided to organize deep learning API. So if we want to organize it in AWS Cloud, usually this is the normal infrastructure of how it looks like. So we start with route 53, like because we want to transform it, connect our request to load balancer, which goes next. Load balancer, which will be connected to our cluster, which will take images from ECR. And within it, there will be an auto-scaling group, which will scale instances based on the load balancer. And we will also need to use spot instances because we want to save money on API requests. So if we decide to use serverless approach in this case, architecture becomes more streamlined. Basically, we just have API gateway and Lambda, and that's it. Or we can connect Lambda to SQS if we want to process queue of jobs in a synchronous way. Alternatively, we can also connect SQS via Lambda to step functions and run inference as part of step functions. And there could be some advantages to it. Basically, when you deploy a new model, one of the challenges is that usually you don't want to deploy it right away. You want to have some rollout process. It could be A/B testing, like just like switching to the new model gradually. It could be like more complex multi-armed bandit, where you want to kind of like manage like when you want to use new or old model. And you can easily implement it using basically step functions, having this pipeline. And it allows to have, as an advantage, modular approach if you need to handle multiple frameworks or multiple programming languages. So let's say you want to use serverless for inference. So one of the questions is how you can import models. Basically, it depends on what kind of files you're using, because Lambda used to be limited in size. So you had to think about like, okay, if a framework is too large, I have to download it from S3. Otherwise, I can keep it like within Lambda, like tflight, Onyx, or Pinvina. So now it's a lot easier because Lambda supports Docker with limits of 10 gigabytes, which usually handles almost all frameworks and all models, except for a case like when you have to have a lot of models together, but then you can use multiple lambdas. So next I want to compare basically inference costs and times. The things which I want you to see here is basically with Lambda we can balance using a large RAM or CPU and CPU, or low RAM and CPU, and usually we can have faster invocations, but they will be more expensive. We will have less invocations per dollar. And here, basically, with your Lambda configuration, it's something which you need to balance is speed versus cost. And it's something which you want to kind of understand, like, where is the balance which you want to strike. Some life hacks for serverless inference if you decide to organize one. Basically, usually it's the case when you want to keep a model as part of your package. Usually it's done like if you want to have high speed because and less startup time. But one of the main things here is that I want to reiterate on balancing RAM and timeout and understanding like whether you want to optimize cost or speed. So where it would work best? The best case is like if you have some new project or pet project or single MVP for your startup, and you don't have a high load, but you want to kind of have simpler infrastructure which will be able to serve your model. Alternatively, if you have a very simple model, then this architecture will reduce cost because you won't have any idle time. And finally, if you have challenge that you have to handle peak loads, then and it's hard to manage clusters, then Lambda will help you because Lambda can scale very fast. So where it wouldn't work? If you want real-time response, or you need a lot of data, or a lot of processing power, or you need to handle extremely large number of requests, I would say more than 10 or 20 million per month, then cluster would probably be a more suitable approach. It will be both faster, and basically it will have, will be able to handle models which have to handle a large amount of data. So there are two repositories which you can check. It's Lambda Packs and GTF Packs, where it has packages for AWS Lambda and Google Cloud Functions with different machine learning and deep learning libraries. So to summarize on the whole thing is that here I try to list like what exists out there and show you patterns, how you can use different services, computing services and different orchestrator services to organize this kind of like pipelines. And basically, it's like a Lego blocks, which you can build based on your context. You need to understand like what is most suitable in your current approach. But the main advantage is that it's very flexible. And if later you want to decide to use different service and you have existing Docker image, then it's very easy to make a transition. So thank you very much for your for your attention, and here are the links to the repositories which I mentioned. And if you have any questions, I would be happy to answer. I think we may have some time because I just want to show a quick demo. Is it okay?
Yes, of course.
Okay, so I mentioned the repository step functions to processing a lot. Just wanted to show you quickly how it looks like and show you how it would work in your AWS account. So here is the, let's say, deep learning training GPU. You have three main files here. First is serverless CML. Basically, it's the main configuration file. It will have like everything which I mentioned. Here you will see like there are Lambda functions which will be deployed, which you can run. Step functions where you basically organize workflow as steps. So you can basically organize each node as a, to define, it could be a Lambda. This node, for example, is a AWS batch where it runs it on custom image and so on. And basically here the parameters which you can use, like Docker image which you want to run, S3 bucket name which you want to provide this Docker image access to, and basically all these other resources you can change it, but basically it deploys AWS batch for you. As you can see, deploying AWS batch is not a very straightforward process, but the advantage is like you can easily reuse it for your application. So here, like the main idea here is to have this kind of as a single deploy configuration file where you can deploy the whole application. The second part here is package.json, which will just have like necessary npm libraries. And finally, index.py, which is basically Python file for lambdas. I will show you how it works. In short, here it prepares parameters for the training job, uploads them to S3, and provides them as parameters later for the training job. And at the reduce step, it basically finds the training results from the model, from the AWS batch, and publishes them. Let me basically, I already deployed it. Usually it takes a couple of minutes, but the process is very streamlined. So you just need to provide input parameters. You can run serverless deploy, and it will deploy the whole stack, the whole application, and provide you with URL to call your workflow. So once, let's say let's call it. So here we will see that execution started. This is the new workflow run. In the workflow, we can see how it goes through the whole workflow. And for each step, we can see the step input and step output. And for the batch, for example, so prepare map step was Lambda, which was preparing the parameters for the training. Now we run AWS batch, which will take some time, and then it will process the results. And publish step does nothing currently, but in your application, it could put data to the database, update some S3 files, and so on. With AWS batch, it's, let me show. So in short, the way, okay, let me refresh. Okay, sure. Okay, we can see that now we registered 3 new jobs because in this step function, we run several training jobs in parallel. And you can see parameter of each training job. And the main advantage is that basically next you can go to CloudWatch and see the logs. So I don't think it will have any logs yet, but from the previous job, you can see that basically anything you post, now you can monitor like how your training process went, what the results, and so on. So basically you can see that although it's not as easy, but you can easily deploy it even for your research or pet project. And like when you deploy this application, you're not getting charged unless you run some job. So that's the main advantage here. I think that's it, and I would happy to answer any questions.
Yeah, thanks. That's a lot of information. And there are questions in chat about slides. And all these links after we finish the stream, I will put all these links in the description. So later you can come back to the same video that you're watching right now and just look at the description. Will be all these links that you can just take them from there. Yeah, thanks a lot. That was very valuable information. And this is actually the first time I see this comparison in terms of price really broken down like per each instance type and this comparison with Lambda. So this is really great. So I was actually looking for this kind of resource for this kind of comparison for quite a while. And so thanks a lot for doing this. This is very valuable. Um, so I want to remind, if you want to ask a question, there is a pinned message in live chat. You can just click on that and use Slido for asking questions. And we already have 9 questions.
Oh.
So I think I will start asking them. In AWS Batch, does it scale across the cluster by optimizing on cores or nodes or the combination of both?
Yeah, it's a good question. So it will scale. It has its own logic. So that's the disadvantage of AWS Batch is that you cannot change logic of how it scales cluster based on job queue, but you can define instance types. And the advantage here is that you can actually define multiple instance types for your job queue. So you can define multiple GPU uh, uh, instances, and it can actually, you can define spot instances, and you can select price threshold, and it will try to select the most optimized, the cheapest instance for your specific job. But that's the main challenge, is that you cannot control the scaling logic.
Okay, thank you. Then we have a question about comparison of AWS Batch and Spark. So the question is, how is AWS Batch different from AWS EMR cluster running Spark applications?
Yeah, it's a good question. So batch, they have different focus. So Spark is like your Spark cluster where you usually have to run like your Spark job. So it's already implies that you're using specific framework. Batch is consider batch is something very close to your usual cluster, but it's basically just scales based on your jobs. But you have to define Docker container here. So batch is kind of like in this Docker world where you just define image and you can run it across different instances. With Spark, it's like you're part of Spark infrastructure and you work with Spark.
Okay, so basically in one case you have to use Spark, right? And you have to write your application using PySpark or whatever. But in AWS Batch, you're not limited to anything. Like you can put anything into your Docker container and just use it, right?
Yes, but batch still exists in this world of like one large job which is processed on one instance, like, compared to Spark, which is basically runs everything on cluster.
So it's is it easy? Let's say you have a job and you need to process, I don't know, 100 files. Can you somehow chunk this in batch? And
Yes,
let's
you
say,
can. Mhm.
yeah.
It's a good question. So basically, you can chunk it like you can create 100 jobs, and depending, like you can actually set up limits like maximum max size of the cluster, and it will otherwise like it could try to create like if you don't put any limit. Well, default limit is 10, but it could create like as large cluster as it wants, so it can create like process it kind of in parallel. But if you have very small jobs, then it's easier to use something like Lambda or Fargate, because then you can be sure that it will create for 100 jobs, it will be 100 machines.
Okay, thank you. So Elias is asking, so the question is, I have trained a TensorFlow model. I have a trained TensorFlow model. It's a CGAN which runs on audio input stream. What is the best way to put it in the cloud? Right now, it's currently running on a server, I assume on-premise server.
It's a good question. So I would say uh, it's easier to start with Lambda just for the simplicity's sake, because it's very simple infrastructure. And I think I have example like in the GitHub repository where you just, because it's like you just deploy Lambda and together with API gateway, and you can use it right away. And if it's trained on, like, you can either deploy it as part of the Docker image, then it will be part of the Lambda. Otherwise, you can use existing package like the one in my repo, but it's probably would be easier if you export your model as TF-Lite or Onyx, because not only framework itself weighs a lot less and you can make model part of the package, but also they both optimize model, so you can, for example, quantize model, or you can prune weights in case you want to make it faster. Or you can export it in OpenWine, which requires some more work, but also like, I think Lambda in this case could be the most straightforward and fastest way to get something in the cloud.
Okay, thank you. So another question from Elias. Why is Worm cheaper if it's faster? So cheaper, more invocation per dollar. So I guess because you pay per each second, right?
So with TensorFlow here is the different, I mean, usually you don't pay for, like, the code invocation here has main meaning that you need to take some time, even if model is part of your package, it takes some time to start the framework, start TensorFlow, and import the model. So here the call invocation is not you don't pay for the time when AWS organizes the container. It's more like a startup time for your application.
And there is also a related question. So why the call to invocation for TensorFlow is actually faster than TF-Lite?
Yeah, it's a good question. With TF-Lite, it's challenging that. So TF-Lite is extremely great at running. Like, you can see warm invocations are very fast with TF-Lite. It's optimized for inference, but because of it, it has higher startup time. So that's TF-Lite doesn't wait a lot, and that's you may seem challenging. Like, okay, TF-Lite waits 20 megabytes, TensorFlow waits 100 like and something megabytes, but with TensorFlow startup time is less, and that's one of the challenges.
Did you say 100? Because last time I checked, it was 1.7 gigabytes.
TensorFlow?
Yeah, like
Oh,
2.3 something. Like it's huge now.
okay. Yeah, maybe I missed some important update.
Yeah, they put so much information there. So much stuff like this tensor board and like all that stuff. Like it's just simply too huge. And even like I'm also surprised to see that code invocation for TF-Lite is shorter than it's fast. Like it takes longer than for TensorFlow, because when you do import TensorFlow, it simply imports a lot more stuff than in terms of TensorFlow Lite. Like just
Well, it's both. It's not about importing the model. It's also about like importing the library, like in your code. It's also about when you start your model, you have to kind of like with TF-Lite, it's starts the model. You have to like invoke it. But maybe I wasn't lucky with Inception v3, so I have this kind of TF-Lite example. So feel free to use it on your model and see like if it will have a better code invocation. But yeah, it's
okay. But this is an interesting observation. So yeah, to be honest, like it's not intuitive. So I would expect because I also experimented with TensorFlow Lite and it was super light and yeah. Okay, so moving on, we have a lot of questions
Mhm.
we which we need to cover. So there is a question about NVIDIA. So how would you compare deploying models in cloud versus such devices like NVIDIA Jetson, if you have any experience with that?
Oh, I never deployed like models to on-premise hardware, so I cannot say. But I think it depends on the case. Like if you have to use on-premise hardware, then you have to use NVIDIA. If you have like if you need to serve a lot of predictions, then you have to use cloud. So it's like usually heavily depends on the context.
Thanks. So, question: can we train on Google Colab or local machine and then deploy on AWS? Is it possible?
Yes, totally. So, yeah, Google Colab, okay, with Google Colab, the challenge will be to automatically use Colab because you usually have to use it manually, like to train. So it would be hard to make it part of your workflow. If let's say you have your local machine, then you can basically organize use the functions as a way to kind of to handle the cloud part. So it will prepare data, then it will get in this asynchronous state. And if let's say you have local machine which always checks if there are new jobs available, it sees that okay, there is a new training job, it runs the training job and has a new model, it uploads it to S3 and calls the functions that okay, I finished the job, and the functions proceeded and it can, for example, update this model, like it can start it can deploy Lambda with this model, it can start cluster with inference, and basically make this like final part of your pipeline to deploy the model.
Okay, thank you. So, Ju, I hope I pronounced the name correctly. Sorry if I don't. Ju asks about Fargate. So, what is the difference between AWS ECS using Fargate and AWS Batch using Fargate?
I mean, can it be switch? Maybe I wasn't following. Actually, yeah, I think. Well, yeah, I think you can use it together. It's a good question. I would say probably they should be similar uh, because ECS on Fargate was mostly for the case where so ECS for Fargate was usually for the case where you had a web server which you wanted to scale automatically and very fast, but it wasn't like really good at handling the jobs because asynchronous jobs because it didn't have like job queue and other stuff. So one of the problems with Fargate is that if something failed on Fargate side, then it wouldn't get retried unless you're using step functions, which then you can use error handling and retry it or some complex logic. So the advantage of using AWS Batch with Fargate is that Batch has own retry mechanism and own mechanism of like what to do if job failed and so on. And it has like job queue. So from this perspective, I would say that Batch is a kind of nicer wrapper because it will have like more logic for handling if something goes wrong.
Thank you. Can you talk more about synchronous and asynchronous workflows? What is the main difference between them?
Good question. So synchronous means that you expect it like the response to happen like faster and like receive the result right away. Asynchronous means that you start some long running job and then the response like won't get to you directly, but something will get updated. So usually the case is like synchronous is an example of REST API. For example, API requests are synchronous. So if you expect to get result right away, if you have some workflow or job queue, it's an example of asynchronous processes.
Okay. Yes, thanks. Could you give a real-time example of model deployment or showing tutorials or Git links where deployment is demonstrated? Perhaps the link you showed us, this like this Git repo, perhaps this covers that?
Yes, it's a good question. So I have here deep learning inference. So okay, this is an example which uses tflight, and you can actually like reuse it like you can basically run serverless deploy. It will package these libraries and run tflight model. So this is like example for that part. There is, I think, another inference, or no, I think it's, yeah, I think it's that's the only inference. If I will double check, yeah, it will also deploy step functions. So it will basically have this like pattern which I mentioned, where you have basically workflow where you want to run two types of models on like two different lambdas. So basically you can just copy this package, update Serverless YAML and index.py to use your model. So you can see that like using tflight is very straightforward. And you can update it to use your model and run it on image or other type of data.
And don't forget to start this repo, right?
Yeah.
So then you can come back and check these results, this code. So we have the last question in Slido, and if you want to ask a question, I again want to remind that it's in the pinned message uh, in live chat. So the question we have currently, it's the last one. Can you please break down? Can you please explain what you use route 53 and gateway for with Lambda? I think you had a slide there where you showed.
Yes.
Yes.
Uh,
Is it to facilitate API calls?
Yes, it's to facilitate API calls. So Route 53 handles DNS, basically that if you have domain name and you want to kind of like, if you want to API, which basic API gateway can already generate you URL, but it will be just like Amazon, AWS, something. If you want to have a nicer API, use Route 53, but you don't like, it's mostly for like, you don't like critically need this part. It's just like DNS part. API gateway is the only way, like, okay, is the main way to have Lambda accept API calls. So it will handle sending requests to Lambda, processing responses, and returning responses to API request.
Okay, thank you. And yeah, I just noticed that there is a question in chat from Ali. Can you get the tuning parameters job from the model that gets automatically created through AutoML? Yeah, is this something that I think SageMaker can do this, right? So SageMaker has AutoML component there.
Yes, so one of the advantages of SageMaker is that it has its own hyperparameter optimization. So you can define hyperparameter and date range, range of each parameter, and it can run the optimization training job. I think it can run like even complex algorithms. I think it can run a Bayesian optimization, but I didn't check it. But
Yeah, I
that's one of
think
the
it's
advantages.
something Bayesian there. So it's not just simple grid search, it's something smarter. Okay, so we do not have any more questions. So how can people find you?
Uh, yes, good question. So, okay, if you want to find me, so there is a link to my website. It has all the contacts, and feel free to reach out if you have more questions or about like repos or presentation.
Yes, thank you very much. That was a great presentation.
Thank you very much for hosting and inviting.
Yes, well, I guess that's all for today. And the next event we have is on Friday. We will talk about public speaking. So see you